এখানে কিছু ভূমিকা করছি না, তারা এখানে ম্যাথমেটিক্সের স্কলার বা ফ্যাকাল্টিজ বা স্টুডেন্টরা বসে আছে, অন্যান্য বিভিন্ন আমাদের প্রতিষ্ঠান থেকে এসেছে। তারা সবাই নিশ্চয়ই এই দুজনের নাম জানেন, ডক্টর নীনা গুপ্তা, ডক্টর অমর্ত্য দত্ত। অমর্ত্য বাবুর সাথে আমার পরিচয় দীর্ঘদিনের। ম্যাডামও আমি বিদ্যামন্ত্রী কলেজের প্রিন্সিপাল ছিলাম, তখন ম্যাডাম গিয়েছিলেন ওখানে বলবার জন্য, সেটাই পার্থদাও আরেকজন স্পিকার ছিলেন। তা আমি অঙ্কের লোক নই, কিন্তু আমার খুব ভালো মনে আছে যখন বিদ্যামন্ত্রী উনি করেছিলেন ঠিক আজকের মতনই একেবারে হল ভরে গিয়েছিল এবং কোশ্চেন আনসার সেশনটাও অনেকক্ষণ ধরে চলেছিল। এটা আমার খুব স্পষ্ট মনে আছে। আমি বুঝতে পারিনি অঙ্কের বোঝার কথা না, কিন্তু আমার শুনতে খুব ভালো লাগছিল যে কত ছাত্র প্রশ্ন করছে, ছাত্রছাত্রীরা প্রশ্ন করছে এবং ম্যাডাম কন্টিনিউয়াস উত্তর দিয়ে যাচ্ছে। মানে এটা প্রমাণ করে, আমি কালকেও বলছিলাম একটা আমাদের কনফারেন্সে, যে জ্ঞানের প্রতি যে ভালোবাসা, নলেজ কাল্টিভেশন, এটা আমাদের দেশের একটা অত্যন্ত গুরুত্বপূর্ণ ক্ষেত্র। কালকেও এটা বলেছিলাম, ভগবদ্গীতায় বলা আছে, নাহি জ্ঞানে না সদৃশম পবিত্র নিয়াবিদ্যাতে, জ্ঞানের মতো পবিত্র আর কিছু নেই। ডক্টর নীনা গুপ্তা এবং ডক্টর অমর্ত্য দত্তকে দেখলে এই কথাটা বারবার মনে পড়ে যে জ্ঞান চর্চাকে কোন উচ্চতায় তারা নিয়ে যেতে পেরেছে, কোন পবিত্রতায় তারা নিয়ে যেতে পেরেছে, যে কারণে তাদের কথা শুনবার জন্য এত ছাত্রছাত্রীরা, স্কলাররা, ফ্যাকাল্টিজরা মুখিয়ে থাকে। সুতরাং বেশি দীর্ঘায়িত করবো না, আমার খুব আনন্দ লাগছে এটা দেখে যে ওনারা আজকে এসেছেন এবং আমি প্রত্যাশা করবো যে যা ডিসকাশন হবে তারপরে নিশ্চয়ই কোশ্চেন আনসার সেশন আছে থাকবে এবং ঠিক একই রকম সেটা খুব ইন্টারেক্টিভ হবে, খুব ইনফ্লুয়েন্সিং হবে। আমি ডক্টর নীনা গুপ্তা, ডক্টর অমর্ত্য দত্তকে এই কলেজ এবং আশ্রমের পক্ষ থেকে, এই বিভাগের পক্ষ থেকে আন্তরিক স্বাগত জানাই, শ্রদ্ধা, নমস্কার, কৃতজ্ঞতা জানাই এখানে আসার জন্য এবং তাদের এই জীবনজোড়া যে গণিত চর্চা সেটির জন্য। বিভাগকেও ধন্যবাদ জানাই। অন্য যারা এসেছেন, ছাত্রছাত্রীরা যারা এসেছেন, ফ্যাকাল্টিজরা বা স্কলাররা, তাদেরকেও একই রকমভাবে স্বাগত জানাই। নিশ্চয়ই একটা খুব ভালো ইন্টারেক্টিভ সেশন হবে। উই উইল এনজয় দিস একাডেমিক ফিস্ট, এটা আমার খুব বিশ্বাস। ধন্যবাদ।
ওনার আমাদেরকে এই কিছুক্ষণ সময় দেওয়ার জন্য অনেক ধন্যবাদ। এরপর প্রিন্সিপাল মহাশয়কে অনুরোধ করব প্রফেসর কুমার দত্ত স্যারকে প্রেজেন্টেশন করার জন্য।
Good afternoon, everyone. Hope you are all enjoying Infinity 2025. Finally, we are present at the most awaited moment to witness and experience the professor who does not require any introduction in the field of mathematics. She was a visiting fellow at TIFR. She solved the long-standing Zariski cancellation problem in positive characteristics in 2013. She was lauded with Shanti Swarup Bhatnagar Prize for Science and Technology in 2019. She was awarded the ISI Ramanujan Award in 2022. Nari Shakti Puruskar on 8th March 2022 by the President of India, TAS Young Scientist Award by the World Academy of Sciences and Chinese Academy of Sciences in 2023. She has received Infosys Prize 2024 in Mathematical Sciences and has been selected by the AMS and AWM as the Emmy Noether Lecturer for the year 2025. Thus, with her groundbreaking research and unparalleled dedication to mathematics, she has earned her place among the greatest minds in mathematical history. So please welcome none other than Professor Neena Gupta.
Thanks to Professor and Professor for giving me this invite, and I am very glad coming here. And I wanted to say something about a very elementary topic, which is sort of, though it is elementary, it's very important because it had led to many applications. So I would like to first thank Professor Datta, who had given several inputs in preparing these slides. Without his help, these slides would not have been possible. I would have written here something else. So let me start with comma. So there is comma, and probably we know about him that by profession he was a lawyer, but mathematics was a passion for him. Now it's supposed that people take mathematics as a profession, but somehow I want to convey that it cannot be a profession, because unless you are passionate about it, you should not enter this subject. It is not a profession. And he was known as the father of modern number theory. At the times of Descartes and Pascal, were leading mathematicians who promoted coordinate geometry and analytical geometry. Fermat was introduced number theory at an elementary level, and he was famous for posing challenges for his fellow mathematicians. Most of the results we probably had a proof of it, and therefore we could have fun. And he contributed significantly to other branches of mathematics, including geometry, calculus, algebra, probability, and other topics. Fermat himself was inspired into number theory by the work of Bachet's translation of Diophantine's work and most of his work which we come to know of today is by the notes of Fermat on this Bachet's book and correspondence of Fermat to other mathematicians. So he himself has never published any paper or written any manuscript, but with written correspondence with fellow mathematicians and notes of his book, we come to know about many of his problems. Now let me introduce what is a descent method. It is a kind of induction. So induction is some topic, I suppose it is introduced right in the school days. In high school days we come to know about mathematical induction. So in induction we increase the number for n equal to 1, suppose the result is 2, then we try to extend it for from n equal to k, we try to extend the result to n equal to k plus 1. Descent is a sort of a reverse mathematical induction, and it is based on the principle that any non-empty set of positive integers has a minimum. So this has two consequences. The first consequence is a method of infinite descent, where we prove by contradiction that a solution does not exist to a problem. So suppose a system of equation has a positive solution, positive integer solution, then by some means we will produce smaller integer q will be greater than p will be greater than 0 because p by q is a number less than 1. So we can square this and get this equation, and with some manipulation is basically q square and minus this, we get this equal k square is equal to q into 2 minus 2p, which will imply that you divide by p, that is q, you get p by q is equal to 2 minus 2p by p, and hence your root 2 minus 1, which was p by q, and p by q is now q minus 2p by p, we got an expression for root 2 minus 1 where the denominator of root 2 minus 1 original was equals q, and we obtain another expression where the denominator is now p, which is strictly less than q. So in this way, if we continue, we can keep on decreasing the denominator, and every time they are positive integers, so this process cannot keep on continuing indefinitely. So thus we have an infinite descent, means decreasing sequence of positive numbers, which is impossible. So root 2 is irrational. That's a contradiction. We know about the Diophantine equation. It is a equation where with some indeterminate and where we are seeking for integer or rational solutions. Diophantine promoted rational solution, and the former as Indian mathematicians were interested about integer solution. It is usually the integer solution which is more difficult than rational solution of some polynomial equation with 2 or more indeterminates, and this term Diophantine refers to the nature of the solution. As the solution is integer solution, it doesn't refer to the kind of problem you are working, so it doesn't refer to the equation. So there are many examples. For example, we have already seen that root 2 is rational. It is equivalent to say this equation x square equal to 2y square has no integer solution. So if this has an integer solution, then you get an expression for root 2. So another famous example of a Diophantine equation is this Pythagorean equation. We know there are several examples, 3, 4, 5, 5, 12, 30. Any solution of this Pythagorean equation we will refer to as Pythagorean triplet. And next is this linear indeterminate equation in 2 unknowns x and y with ABC are integers, and Indian mathematicians including Aryabhatta had given a complete algorithm for solving this equation by a kind of reduction method, and which was again done by Cauchy, and recall that it was Aryabhatta, it was Fermat who was reading Cauchy's note. So he was probably inspired by the integer solution of this linear equation. He promoted Diophantine equations, and this is again an example of an Diophantine equation in 2 indeterminate x and y, where t is an square t and integer. This was studied by Gupta and other Indian mathematicians, including Jayadeva and Bhaskaracharya, and which was revisited in Europe as late as in 17th century, and mistakenly it is known as Pell's equation, though Pell has nothing to do with this equation. So we just see a very quick example of a Diophantine equation, and we call that very quick example. So we proved by the method of descent that this Diophantine equation with 3 unknowns does not have any positive integer solution. So it's again kind of assumption that suppose there are positive integers x0, y0 and z0, which is a solution of this, then first we observe that for any integer n, if 3 is not dividing that integer, then n square will be 1 mod 3, so the remainder has to be 1. So modulo 3, any integer is plus minus 1 or 0. So when you square it, and if it is not divisible by 3, it has to be 1. Now since x0 square plus y0 square equal to 3 z0 square, mod 3 square plus x naught square plus y naught square is 0. And so x naught square if it is 1 and y naught square if it is 1, then you cannot obtain 0 from plus 1 plus 1 or 1 plus 0. So the only possibility is that both x naught and y naught is 0. That means 3 will divide both x naught and y naught. And therefore 3 square will divide x naught square plus y naught square, which is 3z square. So 3 will divide z naught square, and because 3 is a prime number, 3 should divide z. And hence, by setting x1 equal to x0 by 3, each of them are divisible by 3, we obtain a new set of solutions for the given equation x square plus y square for the cases. And thus, for the given set of positive integers, we obtain a new set of positive integers which solve this equation. And note that this z1, what is z1? z1 is z0 by 3. So it is strictly less than z0. So we get an infinite decreasing sequence of positive integers, which is impossible, and hence the equation does not have any integer solution. So this method is similar to the one we have already seen, that root 2 is irrational. Now we classify all Pythagorean triplets x square plus y square equal to z square. This is very elementary, I suppose many of you already know this, but let me quickly go through it. So first we observe that if x square plus y square equal to z square for some positive integers x, y, z, then for any integer rx square plus ry square equal to rz square. So thus, if one solution exists, there exists infinitely many solutions, and we already know that their solution exists 3, 4, 5. So we don't have to worry about whether this equation has solution or not. And now suppose if b is an integer which divides the GCD of x and y. X and y are integers, so we can talk about the GCD. So it divides the GCD of x and y, then one can see that b square should divide z square, and hence b divides z. Therefore, by cancelling out the common factors from all the equations, we can assume without loss of generality that GCD of x and y is 1, and as a consequence it will follow that GCD of x and z and GCD of y and z is also 1. So we have this, that there are positive, we have to find positive integers x, y, z whose GCD pairwise co-prime. Now we know that for any integer n, if n is even, then n square is congruent to 0.1, 0.4, and if n is odd, then n square is congruent to 1, 1. So this is true for any integer, and this is completely classified in all integers as n square is either 0 or n square is 1. Therefore, since GCD of x and y is 1, both x and y cannot be even. Now if suppose both of them are odd, then what will happen? Z square will be congruent to 2 mod. But z is again a square, so it cannot be 2 mod 4. 2 mod 4 is not a solution, which is impossible. Therefore, without loss of generality, we may assume that one of them is even and other one is odd. So both cannot be odd, both cannot be even. So, and we assume that x is even and y is odd. Therefore, automatically your z will be an odd. So we have to find integer values which are solutions of this Pythagorean equation where x is even, z and y are odd, and pairwise they are co-prime. Now from this expression with slight manipulation you obtain that x by 2 whole square is z plus y by 2 and z minus y by 2. Note that z and y are both odd, so z plus y by 2 is an integer and z minus y by 2 is again an integer. X is assumed to be even, so x by 2 is an integer. Now we observe that GCD of z plus y by 2 and z minus y by 2, that is 1. They are integers, so we can talk about their GCD. So if for some prime number p or some integer p divides both z plus y by 2 and z minus y by 2, then p will divide their sum as well as their difference. So what is the sum of this and this? That is z. And the difference of this is y. So p divides z and p divides y. But GCD of y and z is 1. So there does not, so from this equation, we know that each of them, they are co-prime, and there is a very standard mathematical principle that every integer can be written as a product of prime numbers, uniquely expressed as a product of prime numbers. And now, since both of them are co-prime, the set of primes appearing here and set of primes appearing here are different, and this is a perfect square. So both z plus y by 2 and z minus y by 2 are square numbers, because the prime numbers have to, there is a partition between the prime, so x z plus y by 2 and z minus y by 2. So that proves that each of this is a perfect square. So we already have obtained that if there is a solution, then z plus y by 2 and z minus y by 2 are perfect squares. So there will exist a positive integers and n such that n square is z plus y by 2 and n square is z minus y by 2, because they are perfect squares. So solving them, you obtain that z is equal to n square plus n square, y is equal to n square minus n square, and x is equal to 2n. And since the GCD of these two numbers, z plus y by 2 and z minus y by 2 is 1, because they are co-prime, your n square and n square is also co-prime. And therefore your n and n is also co-prime. So we easily obtain that these two are basically co-prime. So m and n is co-prime. Hence both m and n are cannot be even, because if both of them are even, 2 is a common factor. So there is a, and now suppose if both of them are odd, then from this expression, suppose n and n are both odd, then z is even and y is even. So, but GCD of y and z is 1, which will be a contradiction. Therefore, exactly one of m and n is odd. So one number is odd, one number is even. So we obtain, so we can, because we are all positive integers, we assume that n is greater than n. So we obtain that if x square plus y square is equal to z square, which are pairwise co-prime, then there exist integers n and n with GCD 1, and exactly one of m and n is odd, satisfying x is equal to twice n, y is n square minus n square, and z is equal to n square. Conversely, for any set of integers n and n with GCD n and n equal to 1, and exactly one of this is odd, then this triplet x, y, z given by this satisfies this equation, and it also satisfies the properties a and b as well. So in some sense, we have been able to see a complete classification of the solution of x square plus y square equal to z square. So given any positive integers with satisfying this, we obtain the solution. This solution was obtained in the work of Euclid, Diophantine, and the work of Prof in Indian mathematics. Now let's come to the Fermat's last theorem. So Fermat, as we have already talked about him, he used to challenge mathematicians, and he had written this in the corner of his book, this Bachelor's book, that it is impossible, after seeing the solution of the Pythagorean equation from the book of Bachelor, he said it is impossible for a cube to be written as sum of two cubes, or a fourth power to be written as sum of two fourth powers. In general, for any integer n greater than 2, you cannot break it as a sum of 2 higher power. Mathematically, you can say that x to the power n plus y to the power n equal to z to the power n has no positive integer solution for n greater than 2. This had remained a difficult problem for a long time, more than 300 years, and it had reached the development of many branches of mathematics, including algebraic number theory and arithmetic number theory, and of course there were probably one of the proof I have seen in just Google that is one of the theorem which has many number of incorrect attempts, published incorrect attempts, which has a Guinness Book of World Record, this attempt at stage, and we know that it was proved by Andrew Y or the ring of integers are here. But Fermat has given a complete proof for the case n equal to 4 by the method of descent, and we will be seeing an illustration of this proof now. So in fact, for the n equal to 4, a more general statement is true. It says that there exists no positive integral solution of x to the power 4 plus y to the power 4 equal to reduced 4. So we will solve this. So our aim is to find a solution of this. Unlike Pythagorean triplet, we don't know whether a solution exists or not. So we will proceed as if there is a solution. So suppose x, y, u is a solution of this equation. First we observe that if d is GCD of x and y, then d square will divide d. Because you can take out d to the power 4 on one side and d4 will divide d square. So d square will divide d. And now dividing by d to the power 4 on both sides, we can assume that we have a solution which is smaller than the original solution. So x by d, y by d and u by d square are all integers. So we may assume that the GCD of x and y is 1, like the Pythagorean triplets, and as a consequence we will get that the GCD of x and u and the GCD of y and u is also 1. Now observe that since x to the power 4 plus y to the power 4 is equal to u square, your x square, y square and u is a Pythagorean triplet. Right? Because x square square, y square square is u square. So that is a Pythagorean triplet. And now since GCD of x and y is 1, we have a complete description of all Pythagorean triplets. So there exist integers n and m greater than 0, with GCD of n and m is 1, and exactly one of them is odd, such that your x square is twice n, y square is n square minus n square, and u equal to n square plus n square. This is what we have obtained from the solution of our Pythagorean triplet. Okay? Now we just keep this in mind, and so what we have obtained is that your x, y and u, if suppose it's a solution with GCD pair is O prime, then your x square is twice n, y square is x square minus n square, and u is x square plus n square, where GCD of n is 1 and exactly 1 meter is on. Now from this expression, you note that your x is even and y is odd, because the GCD of x and y is 1, and if your integer n is odd, if the integer n is even, then n has to be odd because exactly one of n and n is odd. But then from this expression y square equal to x square minus n square, we obtain that this y square equal to n square minus n square will be congruent to minus 1, which is equal to 3 mod 4. So modulo 4 y square equal to 3, but y square equal to 3 mod 4 does not have any solution. So our assumption that n is even is incorrect. So n is odd and therefore n has to be even. So let n equal to 2k for some integer k and put your k in this expression. We get that GCD of n and k is 1 because, and by 4 we obtain that x by 2 is an even integer. So x by 2 is now an integer. Whole square is k times n, and then we just replace n by 2. So we have obtained some integers k and n, whose GCD is 1, and this equation is this system of equation is satisfied. Now note that GCD of k and n is 1, and this is a perfect square. Again by the same principle, because they are co-prime, the primes will partition the two. So your k and n are perfect again a recombinant triplet. So we can again apply the formula of the recombinant triplet, how they will look like. So there exist integers R and S which are co-prime such that your Y is R square minus S square, 2A square is equal to RS, and B square is equal to R square minus S. Observe that R and S are co-prime and 2A square is 2RS. So A square is R times S. Again a square number. So R and S has to be perfect square. So since R and S is co-prime, R must be a B square and S must be B square for some P and B positive integers. Then, just putting it in this expression, we obtain that T to the power 4 plus V to the power 4, because this is R and S is equal to B square. Recall, this is the same equation of this form, x4 plus y4 equal to a square. And now P4 plus B4 is B square. But B is strictly less than B to the power 4, which will be strictly less than B4 plus 4A square. But that is my integer U. We will use this. So thus, from an integer solution x, y, u, we obtain another solution x1, y1, u1, which your u1 is my integer b, it is strictly less than b. This leads to an infinite decreasing sequence of positive integers u1, u2, which is impossible. Therefore, the original equation does not do this. So this is what Fermat's original statement was a bit of geometry. He didn't say anything about this. Fermat proved that for a right-angled triangle with interior coefficients, the area cannot be a square. And he mentioned that it's my own discovery, though the proof is not much difficult, but I give a proof here as this method will enable extraordinary developments to be made in the theory of numbers. And he was actually correct. He was describing this method of descent, giving a proof of this, and his descent method was the guiding principle for many mathematicians of 18th and 19th, 20th century, which lead to many important developments. So, and algebraic, if you want to write, it says that does not exist any positive integers a, b, c, such that a square plus b plus square root of c square and half a is c square. And this can be deduced from the equation which I have already solved, but I don't want to spend my time on this now. Now I give you another example of this constructive proof. Using descent, giving a constructive proof of something. So I don't know, but many of you may have heard about this, that an odd prime is a sum of two squares if and only p is 1 mod. So the one is quite obvious that if p is a square plus b square, then because p is odd number, so both a and b cannot be even, and one of them is odd and one of them must be even. So when you, and then going on 4, this must be 1 mod, because exactly one of a and b is odd. So if p is sum of two squares positive integers, then p is 1 mod. That is very easy to observe. Conversely, now suppose p is 1 mod 4. Our aim is to construct integers a and b such that p is a square plus a square. That is the aim and target. The first we observe that there exists an integer x such that x square is minus 1 mod. So I just could not write it here, but we know that product of all these numbers is minus 1 mod p for any odd prime. All this. So we know this result? Wilson's theorem. Now your p minus 1 is 4k. So p minus 1 by 2 is 2p. So what is p minus 1? So we can divide it into two parts. And note that this one is minus of and if I call this number x, then this is x into x minus 1 to the power k minus 1 by 2, which is congruent to minus 1 mod t. But minus 1 t minus 1 by 2 is even, so this is 1, so we get x square is congruent to minus 1 mod t. So there is an integer x whose square is minus 1 mod t, because your p minus 1 is 4t. Okay, so thus, if I take y is equal to 1, we have x square plus y square is some m plus m times t, where because your x is less than p, y is just 1, this integer m is strictly less than p. That is easy to see. Okay? Because this is p square. So if your m is equal to 1, we already have a solution for p equal to a square plus b square. We can take x and y, that will be the solution. Otherwise, you can find integers u and v. So this is no longer, need not be positive integers, no longer need not be positive. But you can find integers u and v whose modulus is less than m by 2, such that u is congruent to x mod m and v is congruent to y mod m. So m by 2, just take plus minus 1, so take something whose modulus value is less than m by 2. Now from this you have to see very quickly that x times u plus y times v. X times u plus y times v is congruent to x square plus y square mod m. So this is divisible by n. X times v is cross multiplication minus y is divisible by n. And u square plus v square plus from the expression x square plus y square, it is also divisible by n. So all these three expressions are divisible by n. So there exists. So now initially my x and y are positive, but for the time being let's assume that there are integers x and y whose modulus are less than p, and n is again an integer whose modulus is less than p, such that x square plus y square is less than p. We have obtained integers u and v such that u is congruent to x, v is congruent to y, and we obtain that x plus y and x minus y and u square plus a square are all divisible by n. This is something we have already obtained. Therefore, from this identity, which was also observed by Brahmagupta's computation law, you can clearly multiply and get this, that this identity, and you observe that each of this term is now divisible by n. So we can divide by n square on both sides and obtain pk is equal to this, where k is u square plus a square by n, which is an integer, x1 is xu plus yu by n, and y1 is xc minus y1 by n. So we obtain pk is x1 square plus y1 square, and what is this value of k? This value of k is strictly less than n by 2. Why is this true? Because your mod u and mod v are less than n by 2. So their square will be x square by 2, and then when you divide by n, it will be n by 2. So you have obtained an integer k which is strictly less than n by 2, and it satisfies this. If your integer k is equal to 1, you are done. You already obtained p equal to x1 square plus y1 square. And if not, you repeat the same process with replacing p by n. And finally, it will lead to a solution. So here we have a solution to the problem, not a Because every time when we decrease, it has to count to stop. So the k will be 1 at once. And we will stop. So that will give a proof that p is sum of two squares whenever k is common to 1 1. Now, I so go back to this history in Indian mathematics. He discovered or he illustrated a method of Kuttaka for solving linear equations. So the Kuttaka, this word, has come from the word kut, which means to crush or to grind, and this also has a seed of this idea of descent. For example, there is a kind of divide and conquer strategy which has been used. So, given any problem, it may appear very difficult, but at some stage, what we should always do is that we should try to reduce it as much as we can. So, reduce the problem, kind of whatever we know, we should keep on applying that, and this recursive techniques of breaking down a problem into sub-problems of the same type but of reduced coefficients makes the problem maybe finally at the stage it will become very easy to solve. For example, let me just give you illustrate these principles by one example. So let me solve this equation 10y minus 7x equal to 1. So we have to find integers x and y, maybe positive, negative. But apparently it looks very difficult. If I say to solve y equal to 7x plus 1 equal to 1, can you solve this? Y equal to 7x equal to 1. I can take x equal to 1 and y equal to 8. For the next one, I can take y equal to 1. Y equal to 1 and x will be then 9. So if one of the coefficient is 1, then it's very easy to solve, right? So let us try to force that. So what we do, we make a change of variables so that each time the coefficients become smaller. So this is kind of a reduction. So here we reduce the number 10 by the integer 7. So we divide 10 by 7 and we substitute there. So then from this, one can see that 7 times 1 into y minus x is equal to 3. So if I call y minus x as a new integer z, then the original problem 10y minus 7x is reduced to 7z minus 3y equal to minus 1. Once I make this substitution. So here x is equal to y plus z. Now again, this is a linear equation with coefficient 7 and 3 and which is again big for me. So I will reduce 7 by 3 and divide and kind of obtain a new equation with this coefficients 3 and 1. And this 2z minus 1 I will call some other substitute to a value called w. So we have to now solve 3w minus z equal to 1, where your w is y minus 2z and y is 2z plus z. So once I put w is equal to 1 and then you go backward, you get that z is equal to 2. And from here you can obtain your y is equal to 4 plus 1 is 5. And then from here y is equal to 4 to obtain also the value of x, because x is y plus z. So you go backward, you can get a solution of x. So the originally which was looking difficult, if you keep on applying this kind of descent argument, then reduce the coefficients at every stage, then you obtain the solution. Now this was a question which was posed by us that whether Algebraic's method resembles the celebrated method of Fermat's celebrated method of infinite disk, and which Narendrapur has answered that in later Sanskrit texts this became known as Kuttaka, method, a fitting name, they fall into our mind, Fermat's infinite history. And Dashit, recall it was his translation of the Diophantine work. Dashit solved this linear Diophantine equation following this exactly the same way as this Kuttaka, and Surrey discovered this method and he described in his book of Diophantines, which was read by Prof. And later had said that Dashit solved the integral equation of the first degree by a generous and a very ingenious method, which Narendrapur had again commented that Dashit's method for the solution of the equation, this linear indeterminate equation, had undoubtedly provided a model for Wallace, Prof and Fermat. So that's the end, and there are some references which I followed. So the first one is a kind of a survey of things. The third one is a textbook of elementary level. So I'm open to questions.
Okay, so now we'll be having the question and answer session. Over to you guys.
প্রশ্ন থাকে একটা ছোট একটা কোশ্চেন আছে সেটা হয় তো প্লিজ স্ট্যান্ড আপ এন্ড আস্ক কোশ্চেন এনিওয়ে please. Can the number of variables be increased in the process like
Questions like, so whether the integer is x square plus y square equal to z square. There are other problems like whether the number can be written as sum of 3 squares or sum of 4 squares. So there are counter examples that there are integers which cannot be written as sum of 3 squares. But I think it's Lagrange who proved that every integer can be, positive integer can be written as sum of 4 squares. But yeah.
Anyone else? You?
Here we put the natural number in the power. If we put irrationals, then there are
So in this Fermat's equation, x to the power n plus y to the power n equal to z to the power n. It is a homogeneous polynomial. So to have an integer solution is same as rational solutions. So for instance, if you have k1 by k1 plus k2 by k2 equal to k3 by k2. And you can multiply by the LCM of q1, q2 and q3 and get an integer solution. So obtaining a rational solution is equivalent to having an integer solution.
and when we convert it to the problem, when we convert it into the problem of irrational numbers, then it
Irrational numbers, of course, you can take to root n and root n. Then there is no problem, right? Because you can have any integers take it to the power n, any integer take it to the power n, and take them as root. So irrational numbers, of course, there are solutions. It's just taking them as power, right?
Argue? Anyone else? Okay, thank you.
What a mind-opening experience. here, I would like to extend my heartfelt thanks to Professor Neena Gupta for such an enlightening and inspiring lecture. Ma'am, your insights have deepened our understanding and ignited new curiosity in our minds. It is truly a privilege to learn from someone of your stature. Thank you once again for sharing your time, knowledge and passion with us. We are truly grateful.